After last month's very nice talk about React Native or React-like programming on iOS, I figured it might be a good opportunity to hold a follow-up talk on persistent data structures, which are a big part of Ganz ohne? Oh, das? Better? Now it's gone. Completely gone. Huh? Is it doing something? Yeah. Okay. Okay, so this talk is basically a fusion of two topics. One being protocol-oriented programming, and the other one being persistent data structures. And you already saw persistent data structures in the last month's talk, if you were here. I don't remember them being called that, but you certainly saw them. I wrote a framework for persistent binary trees, and we'll give a brief introduction to what persistent data structures do, how they work, and then give a demo or show some code of the actual framework. If you have any questions, feel free to ask or ask afterwards. I don't care when you ask. So let's start with persistent data structures. What are persistent data structures? And a good starting point is to just look at what's like the formal definition, and then what's the hello world example of a data structure, of a persistent data structure. A persistent data structure basically is immutable, but always working on a copy of itself. It returns a copy of itself, which also is immutable. You're never mutating state. You're always yielding a new variation of your original state. And the hello world of persistent data structures is the linked list, which in the atomic kind of way is just a single element. And if you want to, in the classical linked data structure, if you want to append, you walk the linked list and then append to the end, and append some more. But you always modify the original data structure. You have only a single pointer to hello, which then is recursively pointing to the follow-ups. If you want to do this persistently, you have to invert the way you're linking. And when you start with hello, you actually prepend world to it. And now you have two links, basically. You have one link to hello, so you could have a list of just hello, and you could have a second list of world hello, which shares hello. So there's only a single copy of hello in memory at this point. And if you could do this forever and forever until your memory is full. So the implication of this is obviously that stuff is reversed, and you can only go from world to hello and not the other way around. Otherwise, you would have to modify the existing state to add something new to it, so you can always go back to it. So it's always a one-way road, or at least as far as I know, always a one-way road for persistent data structures. And the way you would realize this in Swift is by a simple enum with a case for none, like the empty element, or the sentinel or terminal element, if you will, and one for cons, which is the name taken from Lisp, where this was invented first. And the cons case takes the value t and another list where it's pointing to the previous state of the list, which for a single element list would be a non-linked list. And the interesting part here is the indirect keyword, which is required because you simply cannot have recursive value types. They would have an infinite size in memory otherwise. So what Swift is doing internally is this is going to be turned into a pointer So the linked list T in cons is actually a pointer to a linked list. You can also put the indirect before the enum, and then everything is marked as indirect. There are some small semantic differences, but at least from the implementation point of view, but it's in the grammar use case, they behave the same. There might just be some performance implications. So how would you use this? You would first start an empty list, and then to create a new list with a single element, you would take the empty list and prepend the one. And to append something else, you would take the list with 1 and prepend 2. But you still have access to empty list 1, list 2, and in the end list 3. And they all share the same memory. Like this initial non-value is shared by all of them. And to make it a bit more like idiomatic and Swift, to create this stuff, you would probably create some initializers, like one for the empty list, and one for a list of a value, and then some optional tail of the list, which is the previous state. And then your creation snippet would look like this. Now, if you wanted to walk the list, you could simply implement some internal iterator function, walk, which takes a closure and then applies it recursively to the elements. This would, of course, create a stack overflow if your list is too long, but like this one fits on the slide, so this that's going to be. You could do it with a while loop, of course, as well. And now, if you wanted to, oh, there's a copy. If you wanted to collect the elements of the list in an array, you could use this walk function, and inside the closure, just collect your array. We will see this later with the trees as well, so this is a nice comparison later. And if you now collect those, you see the elements being prepended. If those were like class elements, you could actually check that the pointer values are the same for each of these ones, for example. Now, this is a list, but if you want to have a tree, you just do this. Instead of having one value you're pointing to, you're simply pointing to 2 values. And the way you would model this is, again, with an indirect case, which in this case would be branch, which would point to another binary tree, a value and another binary tree for the left and for the right child. And the none case in this case would be called leaf, for example. As you can see here, the tree we're going to get would have lots of leaves at the ends, which are not doing anything. It's kind of wasteful, but it makes implementing algorithms a lot more easier, many of them. So it's quite convenient to do this, and they're pretty cheap. Again, the initializers for a tree would look like this. You would have one for the empty tree. Like if you wanted to implement a set based on a binary tree, you would have an empty set like this, for example. And then if you wanted to have a tree which only has the root node, you would have an initializer like this, and then the general case which creates a branch. And now is when protocol-oriented programming comes into place. Because if you define a protocol like this, where you have a binary tree type with an element type, an empty initializer, and then this dubious analysis function, which I'll explain in the next slide, you can have a very lean implementation of your binary tree and share lots of stuff. So walking the tree, printing the tree, and all these kinds of actions can be applied to basically every tree you implement, which could be like a simple binary tree, an ABL tree, a red-black tree, whatever floats your boat. And the analysis function basically behaves like a type erasure on the fact that it's an enum, because you cannot specify enum cases in a protocol. So what we do here basically is we do the switching between these two different cases by providing two different closures for the analysis function. And as you can see later, basically every function in the framework uses this function internally. In the leaf case, it's just calling the leaf closure. In the branch case, it's calling the branch closure and passing the elements. And based on this, we can then implement the equivalent to what for a list was the walk function. In this case, is for example the in-order function, or you could have a pre-order or a post-order for the traversal of the tree, which simply visits the left child first, then visits the node's own element, and then visits the right child last, and does this recursively. Now, if you want to build on this binary tree type protocol and build a binary search tree type, you simply define the element to be comparable, and you add a convenience initializer which allows you to build a tree from a sorted sequence. And this, for example, then would be the implementation of a get function which gets you a certain element out of the tree in case it exists or not otherwise. Again, as you can see, it's implemented based on analysis. And in case of calling it on a branch, you check if the left child is, if the element of the node is bigger than the element you're looking for. In that case, you recurse to the left child. On the opposite, you recurse to the right child, and if it's neither of those, you have a match and return it. If it's a leaf, you obviously don't have a match, and you reach the end of the tree and can stop searching. And then you can extend this with a growable binary tree search, a prunable binary tree search, and a mutable binary tree search, which just fuses those together. As you can see, you're not just inserting, but you're actually inserting and returning a new copy. Like this self in the return type is the new modified tree. And the element, the optional element, is the existing element which might have been already existing at this point in the tree. Okay, I'm getting ahead of myself. So if you want to insert in a tree like this, you would start with an empty tree. And then you insert 3, which is pretty trivial. You just replace the empty root node with a branch in the body 3, which then has 2 empty leaf nodes. And because this is going to be very noisy, I'm just going to skip those in the drawing. So next we insert 0. You copy the root node, and then append a 0. And you have this invisible null leaf on the right side. If you then insert 5, you again copy the root node, but you share the 0. Insert 1, you copy the root node, copy the 0, insert the 1, but share the 5. So far, the sharing doesn't look too good, but the bigger a tree gets, you see that you're sharing basically the entire tree minus the path to the leaf you're inserting to. And so basically, you need a logarithmic amount of exchanges of those values to insert to a binary tree. And you can see this here, where you're already sharing 2 elements and only changing 3 of them. So let's see some code. Okay. So this again is the definition of the binary tree type. And these are all the functions you get for free, because they are defined based on analysis and are basically free for you. So you get stuff like traversal, a generator, checks for emptiness, checks for count, the balance, the height of the tree, all this implemented based on this function, and the aforementioned traversal functions. And a simple implementation of such a binary tree would then simply look like this and get all the rest for free thanks to protocol-oriented programming. And if you wanted to like implement equality, you could do it like this. This, however, wouldn't be equivalent to the equality of the set, obviously, because this takes the actual structure of the tree into account. So if your tree is differently balanced, it's a different tree. So your set would have to implement this a little bit differently. And then for the search tree, basically the same stuff. You get these functions for free, which allow you to search for functions for objects, search for the containment of objects, and stuff like clearing. Just replace solve with a clear tree. They should be immutable, but I figured, well, I'm just going to add this because sometimes it's just easier to use it otherwise, and this is going to be immutable underneath anyway. And if you then look at an actual implementation of such a tree, of like a red-black tree, for example, there are a couple of things you need to implement here. It's not as easy as just a binary tree, but lots of stuff you get for free. And the biggest obstacle you have to get through is this one, which is the rebalancing, which is basically a huge switch which does like 3-level nested matching and then figures out if you have a misbalance and rotates the tree at this point for one position. The ABL tree is actually even more horrific in this regard, like this. But this, even though it looks differently, is actually much easier to implement than the classical immutable red, black, or ABL tree. I initially had it implemented in the classical sense with lots of bugs in there, and this one I got correct on the first try, basically. And now one of the questions with persistent binary trees is, what's the performance? And if we initialize a tree which is pre-sorted, it basically takes like not even half a second. With inserting in sorted order, which is the worst case because it's always going to be misbalanced and has to balance for every insert, it takes a while. For the ABL tree, at least, like 7 seconds about. The red-black tree is better. It doesn't have to rebalance as often as the ABL tree, but it's still not as performant as like a classical red-black tree. But the benefit is you get an NS undo manager for free. You can have the entire history. You could have like 100,000 copies of the same tree, which is the entire history of this. And those copies would share every single element but their path, the path they changed. So you have very good memory compactness of your stuff, even though you have the complete history. And the history is trivial. It's just inherent to how persistent binary trees and persistent data structures work. There's no figuring out what's the reverse operation for an insert or for a delete or stuff like this. You just go back to in your stack of versions, you pop the current one and go to the one before. And so you also get binary tree printing for free because it's implemented on the binary tree type, and whatever you type implements the binary tree type, it's always printable, assuming that your nodes don't span multiple lines. But in general, you get all this kind of stuff for free thanks to protocol-oriented programming. So that's basically it from me. Any questions?
What is actually the RB tree, red black tree? How are the elements inserted and sorted in there?
The ABL tree is like the classical tree, where you basically have a single node which has a left child, right child, the element, and then the current balance or misbalance. Like 0 if it's balanced, and 1 if it's right-leaning, and -1 if it's left-leaning. And after an insert, you check if your balance has exceeded a certain threshold. Usually it's like 2. If it does, you have to rebalance. But yeah, so you have to rebalance every time you exceed 2, which happens in the worst case, like every second insert. And a rebalance is more involved than just like one logarithmic path. And the red-black tree tries to reduce the number of rebalancings by not having just those charts in the element, but a color, which is either red or black. Red and black because when they released the paper on this, their Xerox printer could do red and black. So just a convenience for this, and it stuck. That's also one of the reasons why the searchable binary tree type doesn't have the function which has a value and 2 children in it, because we couldn't implement this for the red-black tree, because you would have to also insert the color, which has different characteristics depending on the children. Yeah. So the red-black tree is generally the one that's being implemented because it's just much faster. Like C++ uses red-black trees, Rust uses red-black trees, and I guess pretty much everyone else. I would have loved to do a comparison, a performance comparison with like Swift's data structures, but sets are hash set based. So, I mean, one is complexity of constants, and the other one is logarithmic. So it's not fair anyway.
The amount of memory you can share when you remove an element, is it similar like when you insert one, or is it different?
Basically, you have to, if you remove an element, you're referencing the tree from the top, right? Yes. And you're updating something here. Yes. So you have to, again, update the path to the top. All the rest doesn't have to know about the change. So it's always this path. And or not this path, but every path to a change.
So you can say kind of like where you edit something, either you insert, remove, or change the value of something. This path is what has to be recreated.
And you find the framework on GitHub. It's called Forest. So far contains 2 different types of trees, and is implemented based on the I think it's Haskell code of this book, which is pretty great in this regard. The only thing is it's lacking the remove implementation. And the remove implementation is slightly more involved than the insert implementation, so this took a while to figure out. But you could pretty much copy and paste this. No, actually, I think this is ML. This should be ML code. So this big rebalancing function, I could pretty much copy and paste because Swift allows for very deep nested matches, which interestingly is pretty much one of, let's say, 2 contexts where Swift totally beats Rust in expressiveness. The 2 ones I could find, one being existentials and one being nested matching on box values, because due to the indirection, you're actually matching values which are somewhere else on the heap, so it's pretty involved. And thus it doesn't surprise that the bottleneck is this rebalancing function.
Hi. So you mentioned it tried with classes, and you said that didn't go as smooth. Is it because you were trying to do it in place, or because?
Yes. There's so many. If you look at the implementation of the left-leaning red-black tree, which is a modification of the red-black tree, which is simplified. Even this is like at least 2 pages. And there are so many edge cases to keep in mind. And it's very difficult to write unit tests for this because the implementation of the sample code you find is like everything in one function. And I wrote lots of unit tests, but even then had lots of cases where it still didn't work. And with this one match statement, it's write-only code, admittedly, but it worked out of the box.
So following up on the question, I think you can implement the same data structures using classes without in place. I mean, without trying to do it in place. So is there a other benefit compared to using enums? So are enums better for some other reason? Or rather than
I haven't tried it persistently with classes, so I can't comment on this. But what I can comment on is that it's due to Swift not yet having references, like value references, the stuff they're proposing in the memory manifesto for Swift, like 5 or 6, or if it's ever going to come. You basically have a problem with iteration. You need to implement internal iterators, like a for each function. It's very difficult to implement an efficient and still safe external iterator, like what's called an iterator in Swift, with the next function. Because in the iterator, you need to keep the current cursor to the tree, but a cursor would be some pointer to a value, which is the entire tree. So your iterator would contain the entire tree. And you cannot just you could say, well, I'm going to pass it to a pointer and store the pointer. But then you could call an iterator on a struct that might have been at some other place in memory already. So there are these problems with moving data structures. Like if you kept the iterator longer than the tree actually exists in memory, there's no connection, right? You would have banged a pointer, which is utterly unsafe. So this was a big pain point. So these traversal functions are pretty easy. Where is it? No, where is it? There it is. Like this kind of stuff is pretty easy. You pass a closure, and then in the in order kind, you actually get a sorted iteration of the tree. But then you still couldn't return, have some continuation kind of iteration there. That's a big pain point. And I tried to implement this in Rust, or port this to Rust last week, but failed with the rebalance function because you couldn't do matching on box values. Because this iteration issue wouldn't be the case with Rust. Cool. Thank you, man.